Welcome. In this video we're going to look at energy. First of all, before we do anything else, I'd like you to write in on the left the 8 stores of energy that you need to know at IGCSE, and on the right try writing in the different transfer processes. Pause the video and do that now. Answers in 3, 2, 1. There we go. So there are 8 stores you need to know. Notice the letters down the left here spell kilogram, kg, cement. This might serve as a useful memory strategy as far as remembering those 8 stores. Note the 4 transfer processes: mechanical or mechanically, electrically, heating and radiation. They're considered processes, not stores at IGCSE, although you'll still see light and sound referred to as types of energy. Really, light and sound, you can think of them as carrying energy. Ultimately, when light or sound hit or come into contact with matter, they transfer any energy they carry back to thermal. But IGCSE, strictly, they're considered a transfer. Hopefully you're happy that the principle of conservation of energy states that energy cannot be created or destroyed. It can only be transferred from one form or store to another. So the total energy in the universe is fixed. Okay, let's just look at this example. Here's a trolley. It's at rest at the top of a slope. Now, we're not going to do any calculations with kinetic energy or gravitational potential energy yet. Just to recap, as the trolley accelerates down the slope, GP is going to be lost, and that's going to be transferred into kinetic energy and some thermal energy, because there will be friction acting, both in the bearings of the wheels, and of course air resistance will be acting on the trolley as well. So not all the GP will be converted to kinetic energy. There's always going to be some transfer to thermal energy. Note that the kinetic energy and thermal energy transferred in total is going to be equal to the GP lost, because energy is conserved. Okay, now let's look at some of these examples. So what I'd like you to do here is look at each statement, try to identify the energy stores which are being transferred from and to, and then try to identify which pathway of the 4, electrically, mechanically, radiation or heating, is responsible. Pause the video now and have a go. Answers in 3, 2, 1. A few things to say about each of these. First of all, B. When an engine actually does its job, the fuel's combusted. That obviously creates heating and heats a gas, which then expands, drives a cylinder, which ultimately mechanically creates kinetic energy or transfers energy to a kinetic store. So this is slightly ambiguous. I'd accept either heating or mechanical. Incidentally, mechanical, or the mechanical pathway, is relevant whenever a force is applied. So whenever an engine applies a force to wheels, or whenever my muscles apply force to my limbs, whenever the earth, as in F, whenever the earth pulls on a pendulum, accelerating it to transfer GP to kinetic energy, then that's a mechanical pathway. For E, you may have written light in place of thermal. Thermal energy is counted as a store at IGCSE. Light is considered a pathway. So what I would say is light carries energy away from the lamp. Ultimately, the light will hit objects, transfer it to thermal. A lot of the time, light is considered still a form of energy. So I would accept light in that space as well. Incidentally, if you want more detail on this categorization of energy stores and transfers, please let me know. On the whole, IGCSE mark schemes will be fairly understanding if you talk about light and sound energy. Okay, next we're going to look at energy flow diagrams. So this is an example for the trolley, which I've drawn above. We've got gravitational potential energy store initially. Mechanical work is done. The earth pulls on the trolley, it accelerates down the slope. Kinetic energy is produced or transferred to, and of course so is thermal or internal energy. Have a go at this example. So this is an energy flow diagram. The green boxes represent stores, the blue arrows are meant to represent transfer processes. So try to fill that in for a smartphone. Pause the video and have a go. Answers in 3, 2, 1. Okay, so this is my attempt. You get electrical transfer from the battery of the smartphone that powers the screen, which then gives off light, which carries energy away, radiation. You also get some thermal energy being transferred. The phone heats up. Ultimately, that will be carried off partly by heating the surroundings, but also by radiation. So you could have another arrow coming off here, heating, because it heats the surroundings, heat's conducted away by conduction and convection. Finally, the electrical transfer process drives a speaker or a loudspeaker, which effectively is providing kinetic energy to a cone, which is oscillating and then producing or radiating by emitting sound. So that's a transfer diagram for a smartphone. Of course, the other diagram you need to be familiar with is a Sankey diagram, so we can actually use this and talk about efficiency at the same time. Now, the main features of a Sankey diagram are that, first of all, you need labels, which tell you the type of energy or the store, and also the amount in joules. In this Sankey diagram, this is to do with a car. You can see that 100 joules of energy start off in crude oil, and we've got energies coming off down the bottom, they're waste forms. The useful form conventionally goes straight on. Now, the width of the arrows has to represent or be proportional to the amount of energy we've got. Now, we're told that we've got 100 joules of energy to start with, and there are 20 squares here, okay, which means that every square is worth 5 joules. Before I continue, have a go at filling in the 3 gaps on the Sankey diagram. Answers in 3, 2, 1. Okay, you can see I've worked those out. We can see that this is 4 squares across, this is 12 squares across, and that's 4 squares across. All these energies, 20 plus 60 plus 20, also add to the 100 we started with. Hopefully you'll remember the equation for efficiency, which I'm going to let you pause and finish this equation now. Three, two, one. Okay, so hopefully that agrees with what you've got. If we use the values we've got here, the useful energy output for our car is 20 joules. The total energy input was 100 joules from the crude oil, multiplied by 100 to give us a percentage. Gives us 20%, that's dead easy. But what's important is the efficiency is telling us what percentage of the energy we put in is transferred usefully or to a useful form, which in this case is kinetic energy. We could also, while we're at it, label the types of energy which are being produced or are involved at each stage of the process. So this will be thermal, this waste energy. This will be primarily thermal, the energy wasted in refining the oil and transporting it to a filling station. Okay, so that covers basic energy in terms of types of energy store, energy transfer. We're going to get into the detail, like the calculations, work done, kinetic energy, GP in a later video. So there's more to come. Right now, however, I'd quite like to talk about heat transfer. So this is something you've done recently, so I'm just going to whiz through this. Before I say anything else, what I'd like you to do on the right-hand side over here is write down definitions for conduction, convection, and radiation. So pause the video and have a go at that now. Answers in 3, 2, 1. Okay, I apologise for my handwriting. Hopefully that tallies with what you got. Conduction, first of all. So conduction involves, and conduction can occur in both solids, liquids and gases. It's to do with energy being transferred from neighbour to neighbour in a non-metal. Okay, so an atom picks up some energy, vibrates more vigorously, its nearest neighbours pick up some of that energy, and then that process continues. So energy is conducted throughout the material. Of course, metals have a lattice of ions, but they also have delocalized electrons, which are free to move throughout the metal. They're not localized to a particular atom. So you can actually get electrons transferring energy or moving towards the hot end of the metal bar, picking up some energy and then being able to move fairly quickly to another part of the metal and transferring the energy to a more distant part of the metal more rapidly. Hence, metals are better conductors, both electrically, but in this context, thermally, than insulators. Another key point is that liquids, but particularly gases, are poor conductors. So remember, conduction is to do with passing energy from one atom to the other without overall movement of matter. So because gas molecules are so far apart, this is not to scale. They're much more spread than that. Then if you were to heat one side of this container, conduction through the gas would not happen very well at all. Okay, convection could occur. Certainly the gas particles could move around, but conduction, passing energy from one to the next, is not going to happen. So a key point is that gases and air is a mixture of gases, are poor conductors. Okay, that crops up an awful lot, as we shall see. Okay, next, convection. Well, let me just go through the basic idea. So if this radiator down here is heating the air close to the radiator, the air in the vicinity of the radiator is going to become less dense. It's therefore going to feel a force upwards, so it's going to rise. That's actually going to leave behind a low pressure area here, into which will be drawn cooler air from the rest of the room. So cool air will be drawn in. This hot air will cool down and eventually it'll fall. But what you actually get forming is a convection current. Now that convection current will continue, if we've got a room here, until the air in the room's at the same temperature. Then there won't be a convection current any further. So that's the idea. Convection occurs both in gases and liquids, and does involve the overall movement of the atoms or molecules which make up the substance. Okay, radiation's to do with emitting or absorbing or reflecting infrared radiation. So if I've got a tin of water, could be a saucepan, it will be emitting infrared, in fact, at all temperatures to some extent. However, if I were to heat it up, first of all, hotter objects will emit more infrared, so you'd expect more infrared to be emitted. It also depends on the colour and the material of the object which is either absorbing or emitting. Okay, as you can see, I've got things written down here. So dark, matte objects, so objects which aren't shiny, are good absorbers and good emitters, but they're poor reflectors, whereas light, shiny objects such as aluminium foil would be poor absorbers and emitters, but good reflectors. It's worth saying that you should never say objects or materials are good absorbers or emitters of heat. You always want to talk about radiation, specifically infrared radiation in this context. Now let's apply some of this to the following situation. So what I'd like you to do, perhaps pause the video and have a go, is to just sketch down some notes for each of these 6 situations, outlining how they're reducing heat transfer. Okay, so pause the video and have a go. Answers in 3, 2, 1. Okay, so hopefully you got some of these ideas down. Things that crop up an awful lot are trapped layer of air being a poor conductor, also preventing convection. If air can't move, it can't carry energy away by convection. Pause the video and just have a read through some of my comments. I might have missed details, but I think I've got most things. Okay, to finish, let's have a look at this exam question. This is a 4-marker, so have a read through this and then have a go in this space here at writing a 4-mark answer. Make sure you write 4 distinct but of course relevant points. Okay, pause the video and have a go. Answers in 3, 2, 1. There are some ideas for you. The main things to talk about are the effect of the cotton wool reducing conduction and convection by trapping a layer of air, the fact there's a lid on top of the container, and then some kind of comparison. Why will B and C, for instance, transfer more than D? And of course, so a comparison between B, C, D and A. A, of course, being the same as D, but without a lid or cotton wool. I hope this has been useful. I'll be talking more about, as I say, work done, kinetic energy, gravitational potential energy in a further video. That gets us started though.